Going to take us to the beginning section 14.2, and it's going to focus on what you see in bold here right in the middle of our textbook. What we're going to be working on is a integral. We've been creating these things called indefinite integrals so far because we integrate and we always take our answer and we add plus c at the end, a constant. But now we're going to create a definite integral where we're actually going to come up with a numeric answer for an integration problem. And we're going to find that over time, and for how we're going to work with this lesson to begin with, you're going to assume a function that lives, as described here, continuous and non-negative on an interval a to b. By non-negative, a good way to look at it is you can say this function lives entirely in the first quadrant. And what we're going to realize is the definite integral of the function f of x over the interval running along the x-axis from a to b is going to correspond to an area under the curve. Could also say, and we'll see this, it'll get extended later as we start to move these functions into not just the first quadrant, but for the moment, what we'll see is the area under the curve bounded by, at the bottom, the x-axis. And that's what we're going to work on and focus on today, that area, and we're going to work through some of the fundamental theorems of calculus associated with that area. Now, to get ourselves started in the notes, I asked you to do the following. I asked you to envision a rectangle with a base of 12 and a height of 6, a right triangle with a base of 12 and a height of 6, and I asked you to tell me what's the area of those two objects. 12 times 6 for the rectangle, 72. 1/2, 12 times 6 for the right triangle, and you came up with an answer of 36. But what we're going to do is we're going to take that same model that you saw in the textbook, again, that's from page 492, the beginning of section 14.2. We're going to take a look at these two little geometric structures that I've built, and we're going to use integration and the principles of calculus to come up with those same two answers of 72 and 36. So here's what I'd ask you to look at. Here is an example. I've drawn a rectangle, I've drawn a right triangle, and I've created the base of 12 and the height of 6 as we've had in both cases. We're good with the areas here. I don't think there's any surprise. But now what I'd like you to do is consider the following. What you see here in black on each of these graphs is I've just kind of superimposed an x and y axis. So this rectangle lives, and sorry for my drawing not being perfect here, you can see that rectangle lives in the first quadrant. This triangle lives in the first quadrant. And what I can do is use this and this as the f of x's that map to what you had seen again on page 492. Let me get to that one more time. So we had various functions, f of x, that you saw in the textbook. Just move the camera. There was our good old f of x. Well, our f of x in our examples is going to become this nice little horizontal line and this nice little line that happens to have a slope of 1/2. So let's talk about these a little bit more. This point is 0, 0, 0, 0, and there's our origin. This point is 12, 0. For this first graph, I have the point 12, 6. And by the way, for the second graph, I have the function, or point 12, 6. Look at my squiggly line. That's what we would represent as our f of x. Well, in this first case, this is just nothing more than a horizontal line. So I'm going to call my little f of x is nothing more than f of x equals 6. And here, what do I have? I have a line with a slope of 1/2. F of x equals 1/2 x. Okay, great. Now, here's what I'd like you to look at. Let's compute the antiderivative of each of these, which would be capital F of x. So I'm going to say f of x equals the integral of little f of x, 6 dx. And if we integrate that, what do we get? 6x plus c. If I integrate, do the same type of concept down here, my capital F of x, well, the integral of 1/2 x is x squared over 4 plus c. So now I have two antiderivatives, 6x plus c, x squared plus 4 over c, antiderivatives for these two nice little functions that are part of my geometric shape. And what I asked you to do next in the notes is the following. I asked you to evaluate capital F of 12, capital F of 0. for both of these antiderivatives and tell me what you get. Well, f of 12 becomes 6 times 12, 72 plus c, minus what? 0 plus c, and I wind up with an answer of 72. F of 12 here becomes 12 squared over 4 plus c, minus, well, 0 squared over 4 plus c, minus c. 144 over 4 is 36, plus c minus c, 36. And what did I notice? I got the exact same answers as I did with just my geometric shapes. So what we're finding is if we can create little f of x as a function that lives in the first quadrant, compute the antiderivative of our function, and evaluate at our two x coordinates to kind of define the shape, the bounds under which we want to get the area, the x coordinate bounds, evaluate at those 2 points, and we can create the area, in this case, the area under the curve, or the area made by this curve with the x-axis. We'll do more of this, but that's our starting point to begin with. And we'll start looking in a second with the continuation of the notes. But the bottom line is I just wanted you to see this basic piece. And what it translates into is what you'll see in a few pages, the fundamental theorem of calculus, which says the integral of f of x dx over the interval where x runs from a to b is nothing more than f of b minus f of a, capital F, in both cases, the antiderivative of f of x evaluated at b minus the antiderivative of f of x evaluated at the point A. This is our key fundamental theorem that we're going to use over and over again. So geometry, basic principle, some very, very obviously elementary functions to work with here. A simple horizontal line, a nice line with a consistent slope, all living in the first quadrant. We're going to start extending this model to more detailed pieces, and we'll start that with y equals x squared as we continue this video. Now on the next page, to extend our knowledge beyond just some simple figures like a rectangle or a triangle. Remember again, we're talking about functions for the moment that live exclusively in the first quadrant. They have positive x, positive y values. Functions won't, obviously functions are graphed all over the place, but again, for our purposes, we're going to be looking for functions that only live in the first quadrant, and therefore we're going to look at the area between the function and the x-axis. It'll be just that area lying under the curve, and we're going to run this from a couple values of x, from x equals a to x equals b. That's the purpose of what we're analyzing here. And looking at these functions, in each case, we're going to have the area under the curve. So the next thing I asked you to do in class is to imagine nothing more than the graph of y equals x squared, and particularly just the part of the graph that lives in the first quadrant. I'll give you a value of a and b, maybe between 0 and 4, whatever it happens to be, and I'm going to ask you, what's the area underneath that curve? And so for our example, I'm just going to consider this function running from x equals 0 to x equals 1. That's kind of what we'll start to do. And the other thing I asked you to work on from an assumption standpoint was, well, the only thing you knew how to measure right now, because you don't have calculators or other advanced knowledge, the only thing you have available to you is the area of a rectangle. And so what you could do with this curve, and this is what the textbook does as well, it's a great example, is they say, all right, well, I'll take this curve between 0 and 1, y equals x squared, and I'll draw some rectangles. And I'll add up the areas of each of those individual rectangles, and hopefully that gives me a good approximation of the area underneath the curve. And so if you look on the top row and the bottom row, you'll see 10 rectangles, 25, 50 rectangles. Now I know 50 is going to be a little bit hard to see, but just go with us for a second. And if you compare the top row to the bottom row, same number of rectangles, but what do you notice? You notice that these set of rectangles here, the top row, underestimate the area. They miss just a little bit. Each little rectangle is a little bit too short. And over here, each rectangle is a little bit too big. And what the book does as well is you keep adding these up, you get a nice approximation of the area. This is an underestimate, this is an overestimate. But as you get more and more rectangles, those little areas that you kind of miss with each rectangle, they get smaller and smaller. The more rectangles you have, your overestimate gets smaller and smaller, how much it misses your true area by. And your underestimate, the same thing. You're underestimating by less, you're overestimating by less. And what we would find is it actually translates, and what the numbers would take us to as you look, you're getting closer and closer to 1/3. And we'll talk about this through the fundamental theorem of calculus in one section. And let's look at that on the next page. Again, remember, area under the curve, positive x, positive y, in other words, quadrant 1, looking for that area under the curve, bounded by two x values, the curve itself, and the positive x-axis. And so what it translates into for any function that we're given to, we can work with this fundamental theorem of calculus. If function f, little f, is continuous on the closed interval from x equals a to x equals b, and capital F is the antiderivative of the function over that same interval, then the definite integral of little f of x dx running from a to b is equal to the antiderivative, capital F, evaluated at b, minus the antiderivative, capital F, evaluated at a. And so tell you what, let's do a little bit of practice real quick with this first problem. We have 0 to 1. Our little f of x is good old x squared. We'd like to compute the integral of x squared dx running from 0 to 1. How do we do that? Well, capital F of x is nothing more than, what's the derivative, the antiderivative of x squared? It's x cubed over 3 plus c. Fundamental theorem of calculus would say, well, compute f of 1 minus f of 0, and that's going to represent the area of the curve. Well, f of 1 is 1 cubed, 1/3 plus c. F of 0 is what? 0 plus c. One of the nice things that happens here, and as you do indefinite integrals, that plus c really kind of doesn't matter anymore, because when you do f of b minus f of a, you're going to have plus c minus c. In any case, what do we get for our final answer? 1/3 plus c minus c, 1/3. And that's exactly what we saw our little rectangles were getting closer and closer to. 0.28, 0.31, 0.323, 0.38, 0.35, 0.34. Getting closer and closer to 0.33. And that's the concept of the area under the curve. So please make sure you understand this concept of the definite integral. Different language, different pieces, but all the same concept. Our textbook, as I said in class, they give you on page 497 a little bit of language that I don't particularly care for. They change variables. So I'd like this to read f of x dx, and I'd say make a note of that just for safety's sake. Now, the definite integral from the fundamental theory of calculus, theorem of calculus, has a number of important properties. The integral of a to b of f of x dx is negative integral of f of x dx from b to a. You're flipping back. This is what? First one is f of b minus f of a. The second one is f of a minus f of b. That's all. That's what the property is saying. If you integrate over an interval that has no length, the integral, the definite integral from a to a of any function is always equal to 0. Moving forward. When you integrate a constant function, we did that with our example with our rectangle when f of x, little f of x was equal to 6. The integral of a constant dx from a to b is nothing more than the constant value times b minus a. We saw that rectangle, 6 times what? 12 minus 0 to get that area 72. If you have a function that turns out to be, you're taking the integral of a function that can be comprised of two different pieces. For instance, the integral of x squared plus x, the integral of x minus 6, so on and so forth. Those definite integrals can be broken up into the sum, or difference of two definite integrals. Integral of f of x plus or minus the integral of g of x. A constant times a function. You can take the constant out of the definite integral. A constant times f of x dx. That integral from a to b is nothing more than the constant times the integral from a to b of f of x dx. And one more piece. Let's say that point C lives somewhere between a and b. The definite integral from a to b of f of x dx can be the sum of two definite integrals, a to c, c to b. Remember though, c needs to be in between. So let's do some work to handle some definite integrals, and we'll do it with some more complicated versions. We already did a definite integral as follows, 0 to 1 of x squared dx. Let's do something where we got to do a little bit more work. And that's what we'll cover in our next video piece. So what we'll now do is work with our first example problem. I'm going to integrate over the interval from x equals 3 to 0, x times, in parentheses, x squared plus 2 squared dx. I could maybe do this through the chain rule and understanding some of the concepts through anti-differentiation that I've worked before, but let's go ahead and use substitution to work through this problem a little bit more in a structured manner. A nice substitution, I'm going to let u be equal to x squared plus 2. You can see that down here. Du dx would happen to be 2x. So let's look at this. Focus, there's our problem up here. And what I'm going to do over here, u equals x squared plus 2, du dx equals 2x. And so if I kind of a first go around, hey, I'll just substitute. I said x squared plus 2 squared. Well, x squared plus 2 is u. I have u squared. Rest of my integral, I haven't changed anything. I've kept my x dx. I've also kept the values of 3 and 0. All those things are still expressed in terms of x. Now, as I want to keep working to do my derivative, or my antiderivative, I got an x dx. So I want everything in terms of u. So look over here. I said du dx is equal to 2x. Tells me that du would be equal to 2x dx. Well, I just have in my integral an x dx. So if I divide by 2, I would have 1/2 du equals x dx. And so my integral can now look like 0 to 3 still. We'll talk about that in a moment. I'm not done with that. 1/2 u squared du. What has to happen next? Well, think. Everything in black is expressed, that isn't circled, is expressed in terms of the variable u. But my 3 and 0 still correspond to what? To x. I need to adjust these bounds of integration to reflect my substitution. So when x equals 3, u is equal to 3 squared plus 2 equals 11. There's my upper bound, now becomes 11. When x equals 0, 0 squared plus 2, I'll go ahead and have a value of 2. Now, everything is expressed in terms of u. And using a couple properties, 2, 11, I'll take my 1/2 out just for the moment and integrate, get the antiderivative of u squared du. What's that become? 1/2 times, what am I going to have? U to the third over 3. And I can do a plus c, but one of the nice things about this is, remember, the plus c minus c, when I'm evaluating, they're going to go away. So for a definite integral, I'm okay with something like this, or this is going to be u cubed over 6. I need to evaluate that where? Between, that's my antiderivative, I need to compute f of 11 minus f of 2. This is my good old antiderivative, u cubed over 6. Well, f of 11 is nothing more than 11 cubed over 6 minus 2 cubed over 6. And just to make it simple, we do this with our calculator, but 11 squared is 11 cubed, 1331 minus 8 over 6. And I'd have a real good answer, 1323 over 6. And again, we'd solve this with our calculator. But the bottom line is, if you're going to use substitution, realize all your variable stuff, everything that you're trying to integrate needs to change and be written in front of you. but also most importantly, your bounds, which originally were written in terms of x, they now need to be written in terms of u, and that's what we'll work through. Now, one other thing you might notice is kind of the notion that I do. I wrote something like this, that my answer was, I'll use u again, 1/2 u squared du is nothing more than, when all was said and done, I came up with, I wrote my f of x, I wrote it as u cubed over 6. And notice I wrote something that looks like that. I wrote my u cubed over 6, and then I have this vertical bar with 11 and 2. That's the same nomenclature as what you see up top here. If you ever see, here's my antiderivative. When you see that vertical bar b to the a, that's nothing, b and a, it's nothing more than capital F of b minus capital F of a. So you'll see me use that concept pretty frequently. Again, with substitution, you need to change everything to work your way through. Could you have also done this with x, and when all is said and done, could you have come back and substituted, oh gee, I'll have x squared plus 2 cubed over 6, and in that case, everything's in terms of x. I could evaluate that between 3 and 0. And by the way, if you did that, what would you still have? Well, 3 squared plus 2, there's 11. 11 cubed over 6. 0 squared plus 2, there's 2 cubed, there's my 8 over 6. I'll get the same thing. So substitution's great. Use it, change all your bounds. If not, get your antiderivative, turn everything back into x, and you can work with the original bounds. So we'll do a couple more examples in the next part of this video. We'll just take a quick break, have you go through this, take a peek at it, work it out yourself, see if you can walk yourself into the same answer. Wrap up with the last two practice problems for this particular section. The integral from 1 to 4 of 2x times 4x squared plus 3 squared dx. Use substitution again. I'm going to go ahead and let u be equal to 4x squared plus 3. du dx is going to be equal to 8x. And so let's do a little bit more legwork. Let me move my camera over a little bit. You can see my setup. And so the first thing I've done, I've gone ahead and put my u in. 2x dx still stays, and I just have u squared. Now, just a quick side note, you don't have to do all this in one step. You can kind of put it all together. I'm just kind of showing it to you in a sequential mode just for safety's sake as you learn your way through this type of concept and this type of procedure. So now I'm kind of left with, well, my integrand values are still be in terms of x, 2x dx, obviously in terms of x. And so what I'm going to do is take a look at what I did over here. du dx is 8x, the derivative of 4x squared. du is the same as 8x dx. But what do I want to substitute for? I need to substitute for 2x dx. That's what I want to put into the integral. Well, it turns out, 2x, what do? 8x divided by 4. That'll get me 2x dx over here. And then I better do what? Divide du by 4. 1/4 du. And so now, the next piece that you see, still keeping my bounds, I'm going to fix that in my next iteration. 1/4 u cubed du. That's what I'm going to integrate. I can, if I wish, I can go ahead and do 1/4 4/1 u cubed du. Excuse me, u squared du. Please accept my apologies there. U squared du. All right. However, what should I do? I should go ahead and account for these integral ranges. 4/1, I need to handle that. Well, when x is equal to 4, 4 times x squared, 4 times 4 squared plus 3, 4 times 4 squared, 64 plus 3, 67. When x is equal to 1, 4x squared, 4 times 1 squared plus 3 is going to give me 7. And so that's what I'm really going to be doing from an integrating standpoint. I'm going to take the derivative of the antiderivative of 1/4 u squared du. Well, the antiderivative of u squared is u cubed over 3. Also multiplied by what? The constant 1/4. U cubed over 4 times 3, u cubed over 12. There's my antiderivative. This again shows my evaluation step. I'm going to evaluate this thing at 67 and at 7. 67 cubed over 12 minus 7 cubed over 12. You'd run that through your calculator to go ahead and get a decimal answer here. And so that's the first problem. All right, spend a few moments, stare down all the different pieces, pause the video if you have to. Let's go ahead now, and in real time, I'll go ahead and work out this second integral. The square root of 2x minus 1 dx, computing that from an a value from x at 2.5 to a b value x equal 5. First things first, u equals 2x minus 1. du dx equals 2. du equals 2 dx. Let's get ready to substitute. I'll do it bit by bit again. 5, 2.5. The square root of u dx. All right. What's left of my integral? That doesn't have u in it. Well, dx. I want just good old dx. Well, 1/2 du is equal to dx. Here comes my next piece. 5, 2.5, the square root of u du with a what? A 1/2 in front. Sorry for my 1/2 here. Let me just clean that up a little bit so it reads a little bit nicer. 5, 2.5, 1/2 the square root of u du. Do one more piece. Handle our 5 and 2.5. So I'm going to move down here. 2.5. When x equals 2.5, I'm going to have u equal to 2 times 2.5, 5 minus 1, 4. When x equals 5, 2x minus 1 is 2 times 5, 10 minus 1, 9. So when I'm going to have this whole thing, now I do have everything in terms of u. I have 1/2. And by the way, I'll write the square root of u now as u to the 1/2 power du. All right. Again, just to kind of clutter or declutter things for a moment, let me do this. 9, 4, and I'll stick the 1/2 out front. I need to integrate u to the 1/2 du. Well, nice power rule here. 1/2, keep that. U to the 1/2, what do I have? Well, I need to remember my 1 over n plus 1. That's the antiderivative of u to the n. 1 plus 1/2. 1 over 3/2, which is the same as 2/3, u to the 1/2 plus 1, 3/2 power. And I have my plus c, but again, since this is a nice little integral we're doing, instead, I'll just go ahead and put my 9 and my 4 bar up. Very quickly, 1/2 times 2/3, 1/3 u to the 3/2 power. Between what? 9 and 4. Okay, let's evaluate. 1/3 times what? 9 to the 3/2 power, which turns out to be 27. 9 to the 1/2 power is 3. 3 cubed is 27. Minus 1/3. 4 to the 3/2 power, which happens to be 8. Square root of 2 is what? Square root of 4 is 2. 2 cubed is 8. Final answer, 27 minus 8 over 3, or 19/3. So these are some good examples of just computing some integrals. We needed to use substitution. Why? Because our integrands turned out to be a little bit more complicated than just something very, very simple for us. When we work and do our substitution, we wind up with integrals in terms of u that we know how to work with. Maybe a power rule. Maybe we'll have the ln of u. Maybe we'll have e to the u. Whatever. It's going to be things basically from our formula sheet that we're very comfortable working with. Work, let your changed variable be your guide, and you can work these problems straight through, and I think you'll become very successful at them relatively quickly.